Hello there. In this video we're going to begin our discussion on the comparison of two different populations. So one would agree that different populations A and B would have their corresponding means, mu A, mu B, and corresponding variances sigma A squared and sigma B squared. So one of the questions that we will discuss, especially in this video, is it possible to test whether these variances for these populations are relatively equal if we pretty much take a sample from A and a sample from B and compare their sample variances to one another. This test is going to be referred to as the F-test or the Fisher test for reasons which I'll discuss momentarily. And in the upcoming videos, we'll perform hypothesis test on whether the means mu A and mu B are relatively equal as well by comparing their sample means x bar A and x bar B. And that's what we'll discuss in the upcoming videos. But in this video, we'll focus on the hypothesis that the variances are equal with the alternative, the two-sided alternative, that the variances are strictly not equal to one another. So to sort of guide this test, we're going to take advantage of a particular property, namely the variable x is equal to SA squared divided by sigma A squared. So that's the quotient of the sample variance of A divided by the fixed constant, the variance of population A, divided by the quotient of SB squared and sigma B squared, same interpretation. So this variable is associated to what we call an F distribution. The PDF for an F distribution is a tad bit complicated, so I'm not going to lay it down here, but the distribution in terms of the graph itself has a relatively similar structure to that of the chi-square distribution. So almost, it doesn't look as wide as this, but it has a similar structure, about equal to this, I say. Alright, so this is going to be the F distribution. Alright, so if this is true, then we're going to approach this problem the same way as before. So there's going to be some region of confidence in the middle. So let's assume we want some middle region of C. So that means there's going to be these corresponding numbers FL and FC. These are going to be called our critical values, same as before. That correspond to this symmetric value of C. So in the middle of this interval is going to be 1, and it's going to be a little bit to the left since it's skewed heavily to the right. So 1 is going to be almost in a non-symmetric middle of this interval. So if you want to use Excel to calculate these numbers, so FL is going to be equal to, according to this picture, alpha over 2 is going to be to the left of FL, and alpha over 2 plus C is going to be to the left of FR, sorry. So this is going to be FR, let me correct that. So if you want to use Excel for these, FL is going to be equal to f.inv of alpha over 2, comma, the degrees of freedom for sample 1, degrees of freedom for sample 2. And FR is going to be equal to f.inv of alpha over 2 plus C, comma, degrees of freedom for sample 1, degrees of freedom of sample 2. So this is how you calculate your critical values for a F-test, confidence interval, or so forth. So if you want to approach this from the test statistic perspective, you can calculate the test statistic, which is going to be equal to S1 squared divided by S2 squared. And you can sort of see whether this number, F stat, lies in between the critical values. If it lies within the critical values, then you fail to reject the null hypothesis. And if it falls outside of the interval, so namely above or below these numbers, then that would be the rejection region. So if F stat is in between FL and FR, then that's where you pretty much fail to reject the null hypothesis. And if F stat is not within our confident or our critical value interval, then that's where we reject the null hypothesis. And I'll go into detail in a minute of what that actually represents. So if you want to go about this in the confidence interval perspective, so according to the probability distribution function, the probability that FL is less than or equal to some variable x is less than or equal to FR, by construction this is going to be equal to our region of confidence C, or 1 minus alpha. So we already know that x follows a particular distribution, namely the one of interest, namely S1 squared sigma 1 squared divided by 2 squared divided by sigma 2 squared. Some people use A, some people use 1, some people use B, some people use 2. It depends on your notation. So this is going to be true, and this is going to be equal to C by construction. So we want sigma 1 squared over sigma 2 squared in the middle. So once you sort of play around with this expression, you're going to get that this is equivalent to writing SA squared. So I'm just going to write A instead, and B instead of 2. This is going to be SA squared divided by FR times SB squared less than or equal to sigma A squared over sigma B squared less than or equal to SA squared over FL times SB squared, and this is equal to C. So this is your confidence interval for the quotients of variances for sigma A squared, sigma B squared. So typically we have written these things in the following manner. So the confidence interval with C level of percentage for confidence for the ratio of variances of A, sigma A squared divided by sigma B squared, is equal to SA squared over FR SB squared. And that's going to be the left boundary. And the right boundary is going to be SA squared over FL SB squared. So the only difference is the location of the critical values. The left is on the right is on the left. So this is the confidence interval for the ratio of variances. So if these variances are equal, then that means the ratio is going to be equal to 1. So remember, the null hypothesis is that the ratio is equal to 1. So if 1 lies within our confidence interval, then we're going to fail to reject the null hypothesis, because that means our ratio of sample variances is pretty much equal to 1 or close enough to it. And if 1 does not belong to our confidence interval, then that means we're going to reject the null hypothesis. So if we reject that null hypothesis, that implies we have evidence to support that the variance of A does not equal to the variance of B. That is, the ratio of their variances is not equal to 1. Okay, with that being said, let's do a quick example of how to walk through this process. So example, suppose that you give the same test to different grades of students. Even though mu A does not equal to mu B by design. So pretty much what are we talking about here? So you give, say, a math test to a first grade class and you give a math test to a second grade class. You would anticipate that their average score is going to be better in the second grade than the first grade. So even though this is the case, you would expect them to perform relatively well to one another within each of their grades, namely the variances of these two. So even though the average is not the same, the level of variation among the grades should be about the same. And maybe you might even put a question mark here because you might not necessarily believe this is true. So what does that claim? Well, the claim here is that the variance of A is going to be equal to the variance of B, where these A's and B's correspond to different grade levels. So if you want to test against that, you're going to say that the variation between these two grades is going to be different. Namely, it's possible that they might be more spread out in grade 2 than that of grade 1. All right, so let's go through this process. All right, so let's assume we want to operate under a 98% level of confidence, forcing our statistical significance to be 0.02. So let's assume we go out and gather a sample. So a sample from A and a sample from B. So sample A and sample B. So let's assume sample A is going to be 48. 48 looks like a 5. 37, 32, 32, 43, 37, and 45. And let us assume sample B constructs of 90, 76, 90, 73, 86, 84, 88, 79, 83, and 70. And notice that these sample sizes are completely different. They do not need to be the same. You might have more grade 2 students than that of grade 1 or vice versa. And there's no necessarily correspondence between these two samples. They are just independent samples in their own right, because nonetheless they're in different grades. If you want to take this moment to pause the video and pretty much put this in Excel so we can work through the analysis, that would be awesome. Else you can just assume that my calculations here are going to be correct. So my sample 1 has 7 people in it, and sample 2 is going to have 10 people. This implies that the degrees of freedom for each of these is going to be 7 minus 1, which is 6, and 10 minus 1, which is 9. And also, if you want to calculate the variance for sample 1 and sample 2, you're going to get that this is equal to 39.81 and 50.54. So you see that these sample variances are different. Typically that's going to be the case. They are going to be different. But the question that we're pretty much trying to ask is, are they significantly different, to imply that the population variances are going to be different as well? Okay, cool. From this level of confidence, let's calculate our critical value. So here's our F distribution. So we need to calculate if this area in the middle is equal to 0.98. What is the left critical value and what is the right critical value here? So our left critical value, so FL, is going to be equal to F.IMV of alpha, which is 0.02 divided by 2, comma, degrees of freedom for 1, comma, degrees of freedom for 2. And you're going to get this is about equal to 0.165. And let's do the same for the other one. So FR is going to be equal to F.IMV of alpha over 2 plus C, comma, degrees from freedom for 1, degrees from freedom for the second. And make sure you stay in the same order for all of these. So once you do that, you're going to get FR is approximately equal to 5.802. All right, those are our critical values here. So now I can construct my confidence interval for the ratio of variances. So my confidence interval, my 98% confidence interval for the ratio of variance 1 divided by variance 2, or A or B, whatever notation you want, is going to be equal to the variance of the first, so 39.81, divided by the variance of the second, which is going to be 50.54, times the right critical value, so that's going to be 5.802, comma, the same exact thing, so the ratio of the first divided by the ratio of the second, times the left critical value, so 0.165. And if you get the critical values switched backwards, then you're going to have a greatest to least instead of a least to greatest interval. So that error should be approximately easy to pick up on. So the confidence interval for the ratio of variances is approximately equal to 0.135, comma, 4.77. And this is the confidence interval for the ratio of variances. All right, so let's go back to our actual problem. So the hypothesis states that the ratio of variances, sigma 1 squared over sigma 2 squared, is equal to 1. So 1 is within our confidence interval for the ratio of variances, so that's good, or bad, depends on how you look at it. So if that is true, then that means we're going to fail to reduce. So that means what? That means we have evidence to support the variation between grade A students and grade B students is pretty much the same, which is pretty much what we had in our mind intended to prove. And that's how you perform an F-test on the equality of variances if you gather two independent samples from different populations.